Graph Theory Class 13 Video 1. In this video we're going to talk about Hamiltonian circuits on the complete graphs Kn. So let's begin with the theorem. The theorem says for n greater than or equal to 1, so essentially for all n, the complete graph Kn is Hamiltonian. The complete graph Kn is Hamiltonian. Okay? So this is the most important part. I can actually get more specific. I can say, moreover, I can tell you exactly how many different Hamiltonian circuits there are. And that's this bit here. So the complete graph Kn has exactly n-1 factorial different Hamiltonian circuits, starting from a given vertex. So this isn't just an exclamation point, like for grammar, this is a mathematical symbol. And if you haven't seen it before, it can be a bit confusing. But what this symbol means is factorial, so you read it as factorial, and what it means is you take the product of all the numbers less than or equal to whatever the factorial is. So for example, 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. And abstractly, n-1 factorial, so n is some integer. This is n-1 times n-2 times ... times 3 times 2 times 1. Whatever this is, okay? I will say, don't worry too much about this notation and about the second part of this theorem. I'm only including it to give you the complete picture, okay? But if you're uncomfortable with this factorial notation, it's not the biggest problem you have to worry about. You should focus on other things. But the moral of the story is that the complete graph is Hamiltonian, okay? And it has lots of Hamiltonian circuits. So let's just do an example, okay? Here's a graph. This graph here is K4. And all I want to do is list all the Hamiltonian circuits. Okay? So I'll draw a table. Well, more of a list. I'm just going to list them all. Okay? And because by the very definition of a Hamiltonian circuit, you visit every vertex once and you return back to where you start, it doesn't actually matter which vertex you start and finish at. So just for consistency, I'll probably always choose to start at the vertex A, just because A is the first letter in the alphabet, but that's not necessarily what you need to do. Okay, so let's try and list all the Hamiltonian circuits. Well, one of them could be A, B, C, D, A. That's a perfectly good Hamiltonian circuit, so I just write A, B, C, D, A. I could also do A, B, D, C, A. A, B, D, C, A. Okay, and I think that's all of them which begin with A, B. So now let's move on to A, C. So I could go A, C, B, D, A. Or I could have done A, C, D, B, A. And now let's move on to the ones that begin with AD. So I can do A, D, B, C, A. And A, D, C, B, A. So you can see it's sort of just a combinatorics game. It's how many ways can you order the letters A, B, C, D, so that you begin and end with A and all the other letters appear exactly once. And if you count them up, we have exactly 6 of them. And 6 is equal to 4 minus 1 factorial, which is 3 factorial which is 3 times 2 times 1. So the theorem works, okay? The theorem works. K4 has exactly 6 Hamiltonian circuits. You could also point out in this example, not all of these Hamiltonian circuits are sort of significantly different. So, for example, I have A, B, C, D, A. That one is right here, A, B, C, D, A. But I also have A, D, C, B, A. This one here. And these two are just sort of like the same, but in opposite directions. One of them goes that way, and the other one goes the other way. So they're different, but they're very, very similar. Okay, and you are able to pair up all of these in this list. One of them, there's always like the backwards direction for the Hamiltonian circuit, but we count them nonetheless. Okay, so that's the end of this example, and that's the end of this video.